Example 17.5. In this example, we have 4 identical power transistors with an aluminum casing that are attached on one side of a 1 centimeter thick and 20 centimeter by 20 centimeter square copper plate by screws that exert an average pressure of 6 megapascals. The base area of each transistor is about 8 centimeters square, and each transistor is placed at the center of a 10 centimeter by 10 centimeter quarter section of the plate. The interface roughness is estimated to be 1.5 microns. All transistors are covered by a thick plexiglass layer, which is a poor conductor of heat, and thus all the heat generated at the junction of the transistor must be dissipated to the ambient, which is at 20 Celsius, through the back surface of the copper plate. The combined convection radiation heat transfer coefficient of the back surface can be taken to be 25 watts per meter square Kelvin. If the case temperature of the transistor cannot exceed 70 Celsius, we need to determine the maximum power of each transistor, which could dissipate safely, and the temperature jump at the case plate interface. In order to solve this problem, we're going to take it to be a steady, one-dimensional, constant properties, and as the problem mentions, all the heat is going to be dissipated through the back of the copper plate, and none of it is going to go through the plexiglass column. Okay, to solve this problem, we're going to use thermal resistances. So we're going to draw this transistor over here, and this transistor is made out of aluminum, and then this is in contact with a layer of copper, and then we have air in the back. So the first resistance that we have is the contact resistance taking place between the aluminum and the copper. So we're gonna just call that RC. And then we're going to have a conduction resistance for copper. I'm gonna call that R1. And then we have a convection resistance from copper to air. We're gonna call it R2. So the first part we're going to do is evaluate the value of RC. And for RC, the contact resistance, we're going to use the thermal contact conductance. And they are related as 1 over HC times A. The value of HC is obtained from table 1.7 from your textbook. We see that we have aluminum and copper in this relationship. Notice that we have a value of roughness, that we have 1.5 microns. This one is the closest that approximates is 1.4, so it's an approximation. And the value of the pressure is 6 megapascals. The value that is given over here is 5. So that's the closest we're going to have. So the value of the conductance that we're going to use as an approximation is 42,000 watts m square K. The area that we're going to use is the area of the actual transistors, which is equal to 8 centimeters square. So we're going to find the contact resistance between the transistors and the copper plate. So it's 1 over 42,000 watts m square K. And the value in meters is 8 times 10 to the negative 4 meters square. That gives you a contact resistance of 0.03 Celsius watts. Now that we have the contact resistance, we're going to calculate R1, which is the conduction resistance for copper. So R1, it is the conduction resistance for copper, and it's simply going to be the length for copper divided by K of copper and A. The value that we are going to use for K of copper, it's given to be 386 watts mK. And the length that is provided is 1 centimeter thickness. And the area that we have is going to be only for one section. So notice that we're doing one section at a time. So it's going to be 10 by 10. Okay. So we replace the values, and it's going to be 1 times 10 to the negative 2 meters. The value of K is 386 watts mK. And once again, the cross-sectional area that we're going to have is 0.01 meters square. That gives us that the value of R1, or your conduction resistance, is 0.0026 Celsius divided by watts. The next resistance is going to be the R2, which is the convection resistance. So it's R convection, and that is simply going to be 1 over the convection value times the cross-sectional area. And it was given that the combined heat transfer coefficient is equal to 25 watts m squared K. And once again, the cross-sectional area that we use is 0.01 m squared. And that tells us that that resistance is equal to 4 Celsius per watt. So now that we have the three resistances, we find the total resistance by simply adding all of them. And that gives us 4.0326 Celsius over watts. The next step that we're going to do is to calculate the value of the power that it dissipates. And that is simply going to be taking the value of Q dot to be the change of the temperature divided by the total resistance. So we know that the maximum temperature that we could have under resistance in the transistor is 70 Celsius, and we know that the temperature from the fluid is 20 Celsius. So that's the delta temperature that we're going to use. 70 minus 20, and this is Celsius, and this is going to be divided by 4.0326 Celsius over watts. That gives us a value of 12.4 watts, and this is per transistor, right? So this is the value that each one of the transistors is going to be able to dissipate safely, so that the temperature doesn't go over 70 Celsius. The next part that we have to do is calculate the temperature jump that it takes place at the interface. So basically at that point, what we're going to use, we're going to use the same value of Q. So we're going to find out what is the temperature jump over here at the interface. So we use the same value of Q dot, and then we're going to calculate a delta T divided by the resistance at the junction or at the interface. So the delta T, and let's call it juncture so that we know which one is it, not to confuse it to the one before. So we got Q dot times the contact resistance. So we got 12.4 watts and 0.03 Celsius over watts, and the value is the jump, it is going to be 0.37 Celsius, right? So that tells you that in between going from aluminum to copper, there is going to be a change of 0.37 Celsius. So if we know that the aluminum temperature is 70 Celsius, then we see that the temperature of the copper is simply 70 minus 0.37, which is equal to 69.63 Celsius. This shows you that there is a very small jump in temperature, and the reason is that the value of the resistance is very low.